introduction, Celine, and also thank you for inviting me to this really nice workshop. So I'm actually learning a lot, even though I'm not coming out of the field. The talks are really excellent. So, and this is just my first day. Yeah, so I'm a junior professor. My name is Katharina-Sophie Isleif. I'm a physicist coming from gravitational wave detection. I studied in Hanover, and now I'm a junior professor for mechanical engineering at the Helmut Schmidt University in Hamburg. This is one of several universities which exists in Hamburg. And my expertise is mainly high-precision optical metrology systems for gravitational wave detectors or other systems, actually. And today I'm giving a talk about gravitational wave detection in general, and then I will focus on the Einstein Telescope. So I'm speaking here on behalf of the ET community. This is not my work. This is the work of the full community in Europe, developing the next generation of gravitational wave detectors. So this is working. As you're maybe not all familiar with gravitational waves, so I will give you just a very short introduction about gravitational waves and what gravitational waves are. Maybe you are familiar with Newton's law of gravitation. This is a classical view of gravity. So you have two masses, for example, Apple and the Earth, and you have an attraction, a force between these two masses, which also depends on the distance between these two masses. But this leads to objects dropping or falling down to Earth. So the more massive mass wins and attracts the apple. And this classical view can explain this future based on Newton's law. It can also explain why planets are orbiting our sun and so on. But there are some limitations. So it can, for example, not fully describe the movement of the planet Mercury around the sun. And this was also one of the motivations for Einstein back in 1915, where he defined something that we call the four-dimensional space-time. So since then, we are not thinking about space and time as separate objects. We combine them in one four-dimensional system or space. And this is also the basis for his general relativity. And as you can see here, this equation comes out. And on the left-hand side, you see the so-called Einstein tensor, which gives you the geometry, the four-dimensional space-time, or more precise, it tells you how the curvature of space-time is changing. And on the right-hand side, you see another tensor. This is the so-called stress-energy tensor. And this tells you how matter and energy is distributed in space, or space-time. So what happens if you put a mass in space-time, it will influence your space-time. So the space-time is not flexible. This is what comes out of his general relativity. It is flexible, like the Earth is an elastic medium. Also, space-time is an elastic medium, and matter changes space-time based on this equation. Also the other way around. This is an equation, so also space-time tells matter how to move. So this is a cycle. So if we have now matter putting into space-time is getting curved and tells other planets how to move. So as stronger the mass, for example, the solar mass, as stronger is the curvature, and other planets follow this curvature. Now you can try to solve these equations. These are the Einstein's field equation. You can try to solve them. It's not easy, but you can find some solutions. And one solution was, for example, the prediction of black holes and other cosmological objects. Another solution is gravitational waves. So gravitational waves occur if you have two massive objects in your space-time and they are moving. They are, for example, orbiting each other. Then they just don't produce a static gravitational field or a static curvature, but they produce ripples in space-time. So the space-time is oscillating, and this is what we call a gravitational wave. And in principle, this can also be described, for example, if you imagine you have 2 points in space-time, 2 test masses, I will call them later. So the distance, the absolute distance between these 2 test masses will change if a gravitational wave propagates through space-time. So you have a baseline, delta L, and this will change due to gravitational waves by a small fraction, delta L, and the strain of the gravitational waves is not larger than 10 to the minus 21. So we are talking about really tiny strains. This is not a correct picture, but since you're a seismologist, I wanted to advertise that gravitational waves are maybe not so different from seismic waves and actually simpler. So as I just learned, gravitational waves exist because we live in an elastic and a flexible four-dimensional space-time. Seismic waves exist because of an elastic solid, for example, where you also solve wave equations, or you have wave equations in the end. For gravitational waves, we need very massive sources because the space-time is quite stiff. So we need really huge sources which can produce these ripples in space-time. So we are talking about black holes, we are talking about neutron stars, we are talking about galaxies. So cosmological objects which cannot be found on Earth. They propagate with the speed of light, which is quite fast. So this is also, so gravity is a fast interaction. And as I just said, it's simpler than seismic waves because we only have two polarizations. So either plus or cross polarization. This is all. The main disadvantage or the challenge is that the strain is relatively low compared to seismic waves, even though we are in the same frequency range. So I put here some dots because we don't know where gravitational waves might occur. So there are some cosmological theories that predict, for example, black holes also from other systems at the high frequency end or at the low frequency end from very, very heavy objects, but we haven't measured them yet. So we don't know what exists out of these frequency ranges. And in the end, you need some detection. For seismic waves, you have seismometers. For gravitational waves, you have highly precise measurements. And I will focus on laser interferometers, even though there are also other ideas how to measure gravitational waves. But the laser interferometers are used to measure displacement changes, so this delta L, which is produced by a gravitational strain. And this is really challenging. So this is just a picture. If you take the Earth and the Sun, which are separated by 150 million kilometers, this distance, if a gravitational wave is propagating through the screen, will just change by the size of an atom, 10 to the minus 10 meter. So, and this is what we need to measure to get to these strains. So we learn space-time is extremely stiff. We need very massive objects, heavy masses, and we need really precise instruments to go there. And let me give you two ingredients that every gravitational wave detector based on laser interferometry needs. So first of all, we need free-falling test masses. We need masses in space-time which just follow space-time. And this is actually one of the most challenges, the most problems or the highest problem on Earth, because you cannot just put a mass in space because it will drop because of gravity. So what we typically do in ground-based detectors is we suspend these test masses. These are mirrors. For example, here a 40 kilogram test mass mirror in the LIGO detector in the United States. And they are suspended by really, really thin silica glass fiber cables. So like thin like a hair, because they need to be decoupled from any motion. So as thin as possible, but of course it must somehow carry the 40 kilograms. And then you have something like an isolation or pendulum system, and above the resonance frequency, your test mass is free falling. So it is really only following the space-time. You can also do other tricks. You can go into space. There you don't have gravity, so your test mass is just following the geodesic, where the satellite or it's brought to. And this is the principle for space-based gravitational wave detectors. Prominent example is LISA, the Laser Interferometer Space Antenna. This is where I did my PhD thesis in Hanover on. Here's just a picture of the LISA Pathfinder satellite, which was launched in 2017. Yes, and was pretty successful. So the plan is that LISA will hopefully start within the mid-2030s. And then we have a huge laser interferometer in space. It's actually the same technology that is used for GRACE follow-on, maybe you know this. So here you have two test masses, which are in principle the satellites. And if the satellites are orbiting the Earth and you have a mountain, so a higher mass, you have this Newton force. So the one satellite will be attracted towards the other one and the distance is changing. Same principle. So This is what I did during my PhD thesis. This is the first ingredient. Now I already talked about laser interferometry, so we need something that measures displacement changes between free-falling test masses once we have them. And yeah, this is a typical scheme of a laser interferometer. You have a laser which is split up on a beam splitter, and if the mirrors are moving, you can see how the output of the interferometer is changing. So the laser consists of an electromagnetic wave in principle. It is reflected from a mirror with very high reflectivity. So these are the 40 kilogram suspension mirrors. And then you overlap two electromagnetic waves, and they produce either destructive or constructive interference, and your interferometer output is getting lighter or darker in dependency on the phase between these two interferometer arms, let's call it like this. However, we need to get these numbers 10 to the minus 21. So on the Earth, we can maybe produce or build detectors on the kilometer range. So we need to measure down to 10 to the minus 18 meters. So this also means that the mirrors are not allowed to move more than 10 to the minus 18 meters, which is quite a challenge. So we are talking here about subatomic displacement changes. However, this was possible actually. So the first detection was made by the two LIGO detectors in the United States in 2015. And this is actually the real data, which is shown here. And I will just show you how it not looks like, but how you can hear actually a gravitational wave. I hope it is working. The second is filtered. This is the raw data. So, and what you have just heard was a merger of two black holes. So very short. It doesn't look like, I mean, it looks really easy. This is time, this is frequency. In seismology, you have way more complex frequency time plots, I believe. And it was measured in both detectors in the United States. You can see here it was like a fraction of a second, the duration in the detector for both systems. And you can see also that the frequency goes up like 400 hertz or so. So black holes with 29 solar masses and 36 solar masses were orbiting each other 1 billion light years away from us with a rate of 400 hertz. So really, really fast. And they approach each other, and at one moment, the distance between those two is so close that they overlap. So they are getting one object, they merge. And in the end, they produced a black hole with 62 solar masses. So there are some solar masses missing, and these solar masses is the energy that produces gravitational waves. So we need a lot of energy, several solar masses, to make the space-time oscillating. And since then, several detections were made by LIGO, by the two detectors. And since 2017, we have also a third detector, Virgo in Italy. And you can see here, actually, this is the first signal that we have just heard. It was the brightest one. It was the clearest one, and we actually needed no filter techniques to see that this is the gravitational waves. While for the other one, it was a little bit more difficult. And here you can also see not a black hole merger, but a binary neutron star merger. And you see that this signal is like 40 seconds long in the detector. So also other sources, but they are quite rare, and they have also less strain, so they are currently difficult to detect. And from these systems, we also expect like electromagnetic radiation. So if you have now another telescope for astronomy, you can also point towards these kind of systems because they will also produce visible light. Here's just an overview of what we can expect. So this is the frequency of a gravitational wave. This is the characteristic strain. Here's the 10 to the minus 21. And the signal that we have just heard was here in this area, and this was the LIGO sensitivity curve. So this is the noise level that we can achieve, and you can also see that the signal-to-noise ratio was quite high. So we were really lucky that this event was so massive. Yeah, and as I told you, Virgo in Italy just joined in 2017, so now we have like 100 events or so. So Virgo is now also part of this network. And by end of the year, also the fourth detector might be online. This is a Kagra detector in Japan. And this is one of the first detectors which will be underground. So it's built in a mine, in a mountain. But you can also see that most of these detectors are in a very broad or narrow frequency, not broad, a narrow frequency range. Here in the audio frequencies, like a couple of 100 hertz up to, yeah, maybe some fraction of a kilohertz. But there are also other sources, for example, especially here in the low frequencies and so on, and we are just covering the upper area. So this is why we are planning new detectors. So this is, for example, the planned detector, the Einstein Telescope, which will have a larger arm length, for example, and also a slightly different constellation. So you can here always see the L shape of a typical interferometer with 90-degree angle. So this will be a triangle with 60 degrees. Very similar to the LISA detector in space, I already mentioned it. In space, you can go much larger, 2.5 million kilometer arm lengths. This also means that you don't need to measure as precise as on Earth because you have these very long arm lengths. So the delta L that you need to measure is only 10 picometers. This is the size of a gold atom. However, this is challenging for this kind of technology because this interferometer, so the 2.5 million kilometer, is not stable. So you need to measure picometers while the satellites are moving, like a car. So, but other technology. I will focus on the Einstein Telescope now during my last few slides and give you some impressions on how do we get down from the current ground-based detectors to the Einstein Telescope. The goal is, or if we go down, or if we can achieve this, we can actually make the detection rate much higher. So for the Einstein Telescope, for the current detectors, we have approximately 1 event per week. For the Einstein Telescope, we will have 1 event every 10 minutes. This is just because we go down by 1 order of magnitude and think about the universe, it is like a sphere. If you now make the sensitivity better by 1 order of magnitude, you increase the volume by a factor of 1,000. And this also means that we are looking back in time because the universe is expanding. So as more we can look out, as more we look into the past, which is quite interesting. And here at low frequencies, we aim actually for 6 orders of magnitude improvements. And this is motivated by each signal which appears in the detectors existed before. It is just here for a fraction of a second. But if we have better sensitivity at low frequencies, we can detect it earlier. So 1 to 3 hours earlier before the merger. And then we can also tell the other telescope or other visible telescopes to point to the correct position in the sky, for example. So a lot of motivation. How do we do this? How do we go from LIGO detectors? Here's a current sensitivity to the Einstein design sensitivity curve. Factor of 10 over all frequencies and an improvement by 6 orders of magnitude at low frequencies, which is quite challenging. So we need a very dedicated site or concept. And the most crucial thing is the infrastructure and environment, actually. Otherwise, we cannot achieve the sensitivity. So the Einstein Telescope will be built underground, away from any seismic noise, anthropogenic noise, away from civilization, to suppress anything above, to oppress surface waves, also clouds and weather and so on, and also atmospheric pressure waves, for example. And it will be longer, as I told you before. It will have an arm length of 10 kilometers. LIGO had 4 kilometers. This is the longest interferometer that we currently have. We cannot go so much longer on Earth because of Earth curvature. And of course, it is also much more expensive. Everything is housed in vacuum tubes, vacuum chambers, and so on. So this is just a compromise. But we need to go longer because we need a longer antenna for lower frequencies of gravitational waves. With a single detector, you cannot measure the 2 polarizations of a gravitational wave. And since we don't want to build Einstein Telescope twice, we choose these triangular constellation. And each of these colors, here for example, the red one, the green one, and the blue one is one detector. So this is now not L-shaped, but 60 degrees, but we have 3 detectors which share the same tunnels and the same stations, which makes it cost effective. Furthermore, we have these dotted lines. So each of these detectors, blue, red, and green, consists of 2 interferometers actually. So we have 6 interferometers in total, which we call 3 interferometers for the high frequencies and 3 interferometers for the low frequencies. Because we cannot design a next generation gravitational wave detector which is sensitive at all frequencies. So it is the noise sources compete against each other, and we need to tackle this by splitting up the interferometer. And this is what I present you now in the next slides. What is limiting us at high frequencies is laser power. So we need to increase the laser power in the Einstein telescope if we want to get down to the sensitivity. And this is also the main reason why we split one interferometer in 2 parts. So at high frequencies, we want to reduce which is called shot noise. So light is not only an electromagnetic wave, it's also a quantum, it has photons. And these photons arrive statistically, so they don't have the same arrival time or the same distance between each other, but therefore they produce statistical fluctuations on the photocurrent or photovoltage in the end. But these statistical fluctuations can be decreased if we increase just the number of photons, the number of light particles. Then we can get down with the shot noise. And the shot noise is limiting us at high frequencies. So we increase the laser power and this will automatically go down. But if we increase the laser power, another quantum noise appears because this is a radiation pressure noise. If you increase the laser power, you will start moving your mirror. And this is a noise source which is dominating us at low frequencies. So here we want to reduce the power. And these two together form the so-called standard quantum limit. There are also technologies where you can, for example, tackle these two noise sources not only by increasing power and reducing power, but also squeezing lasers. So there are also investigations going on. However, we split them up. High frequencies, we use an interferometer with high laser power. And for low frequencies, we use an interferometer with low laser power. And this can also deal better with, for example, stabilization systems regarding thermal noise, because if you have laser power, you have a thermal noise issue, your mirrors are heating up, so you need to cool them down. This is all shifted now to the low frequency range, because these are all mid or low frequency noise sources. So we can somehow decouple these two problems from each other. So this was the high frequency range, and the mid frequency range, we are limited by thermal noise, as I just mentioned. So especially for the high power system, we heat up the laser, the mirrors and so on. So especially for the low frequency, we need a cryogenic system, because there in the ET low frequency interferometer, we will be limited by thermal noise. So we will build, of course, these vacuum chambers and a huge cryogenic system which can cool down the mirrors down to 10 to 20 Kelvin and the suspensions as well. This brings some other challenges. For example, we have figured out that we cannot use, normally we use fused silica as a mirror because it has excellent properties for 1064 nanometer wavelengths and so on. But we have figured out that the mirrors have not a good Q factor. So the pendulums are getting worse and the seismic isolation is getting worse just because of the material. So we need to switch materials. So it needs a lot of technology developments to go there. And of course, if we have a cryogenic system, another problem occurs because we will insert vibrations of the cooling system. So this is what we need to also investigate. And these vibrations actually is also a noise source which is then limiting us at low frequencies. So for example, at 3 Hertz, we need something like 5 to 6 orders of magnitude improvements compared to the current detectors, which is really a lot. And there we have these vibrations. We have also the resonances of the suspensions, which are currently in the LIGO detectors. We have seismic surface waves, if the current detectors are built on the surface. And we also need to go further down, like for example, tilt coupling, earthquakes, microseismic peaks, because we have so-called stray light in our interferometer, and the stray light is a nonlinear process. And if the mirrors or also the vacuum chambers vibrate at very low frequencies, the effect will be aliased in the frequency band that we are interested in. So we also need to suppress at very, very low frequencies, therefore. But this is a different story. So why are seismic waves now so important for gravitational wave detectors? So assume the easiest picture is you have now 2 suspended mirrors in a gravitational wave detector, and in principle we measure the time of flight or the length change between these 2 mirrors. And if a seismic wave is shaking our mirrors, we have in principle 3 problems that need to be solved. First of all, the displacement will change between these 2 mirrors, which leads then to a length noise of our interferometer arm. Then the angle of the 2 mirrors will change between each other, and the full system will move. And if the full system is moving, it will get additional energy, which needs to be solved. So we have an additional energy motion into the isolation system, for example, so we need more damping, the system heats up and produces thermal noise and so on. So these are the 3 points that we somehow need to tackle in gravitational wave detectors in general, and especially for the Einstein Telescope. Therefore, the site for the Einstein Telescope is the most important thing. Currently, we have 3 sites, one in Sardinia, Italy. Another possibility would be in the Netherlands or on the 3 countries, so like Netherlands, Germany, and Belgium, or in Germany in Saxony. This is a 3rd possibility. This is also a little bit now coming up because we got a new center for astrophysics in East Germany, in Saxony, where we also built an underground seismic lab, actually with seismic sensors and distributed fiber sensing and so on. And they were now also investigating the site in Saxony, which looks actually not too bad. But in the end, to be honest, it might be a political decision. So here you can see some site characterizations that are going on from the Einstein Telescope collaboration. And here you can see in orange, this is the acceleration power spectral density of the Virgo site in Italy. And you can also see some measurements in the Netherlands, which is here on ground, on the surface. This is the pink line. And if you go, like here, 250 meters is the blue line, underground, you can actually gain at least 2 orders of magnitude. At the higher frequencies, actually more. And yeah, but what you can always see, here's a plot of again, from the Netherlands side, you can always see, even you go under 250 meter underground, this is here the bottom line, you can still see variations depending on day and night time, and also whether it's a working day or not, in 250 meter depths. And this is some of the problems that we see here. So once we have decided on a site, we need still isolation of test masses. And in principle, we can conclude that we have, for 2 reasons, the isolation of test masses. First of all, we want to have a free-falling test mass. We need to decouple it from ground. And we need suppression against seismic waves, seismic noise, and so on. And each test mass in the Einstein Telescope, we have actually 2 for each interferometer, must be controlled in all degrees of freedom. And this is, of course, not an easy task. And if you do so, you can take your seismic displacement on your site, you have your transfer function of your seismic isolation, and then you can determine what is the contribution to the overall noise in the detector, and came up with such a line like for the LIGO detector. It's a little pixeled, I'm sorry. And we have two kinds of seismic isolation systems that we already use in LIGO detectors, passive and active ones. So the passive ones are just mechanical oscillator, but several levels, so cascaded ones. And here you need to be careful, because if you couple different mechanical oscillators to each other, you need to be careful to choose the right masses, because you have mechanical back action which needs to be accounted for and so on. But we also use active isolation system for feedback and feed-forward control, mainly also in combination with inertial sensors that then measure the disturbance, vibration, whatever, and this is then used as actuation signal for the control of the test masses. And the inertial sensors itself are, again, mechanical oscillators, like, for example, seismometers, which are placed on platforms and so on. And here's just a sketch of the Virgo super attenuator, which is also the baseline for the Einstein Telescope. So this is a cascaded pendulum with in total 6 stages. So you have 6 pendulum stages. We need to make it a little bit longer, from 9 meter to 70 meter, to get the suppression. So we need extremely high tunnels, which is, of course, expensive. We have additional cantilever springs for the vertical isolation at low frequencies. And we have inverted pendulums for the low frequency, so the whole platform is put, so the platform for the suspension is put on these inverted pendulums to get an additional suppression factor at low frequencies in the horizontal. Yeah, and all of this is together with some active feedback control systems included. So we have, for example, sensors to get rid of the chain modes and so on that we analyze. Yeah, and here, this is again a little bit pixeled here, you can see a measurement of the Virgo detector. Here in blue, you see the seismic noise. This is now a meters per square root hertz. And here you can see what the super attenuator is producing. So you gain at 10 hertz, 14 orders of magnitude suppression from seismic noise. And compared to other detectors, this is the best seismic isolation system what we currently have. So here you can see in blue the LIGO and Virgo detector. In violet is the Virgo super attenuator, and the green line is the projected seismic noise suppression or the isolation system that we would require for the Einstein Telescope. Okay, I think because of the time, I will just skip the slide. So we use seismometers for the inertial sensors, which will be replaced later by optical readout to make it more precise. But I want to come to another noise source at low frequencies, and the follow-up will be given on Tuesday in my talk. However, I would like to advertise it now, because here at low frequencies we have not only seismic noise, but we have also so-called Newtonian noise. This is a completely new noise source which comes up in the Einstein Telescope, because we aim for very low sensitivity. You can see that the LIGO detectors are not limited by these kind of noise sources. And this kind of noise source is produced by seismic waves. So imagine that you have a seismic wave which is propagating through Earth. It will produce mass density fluctuations. And if you have mass changes, your force will change. So the force of one point here in the ground will attract your test mass. And this is therefore a direct consequence of seismic waves, but it bypasses all isolation systems because it has a gravitational nature, so to say. And this leads to test mass accelerations, which can be described by this formula. Here, for example, is the seismic displacement put into this equation. Here you have the test mass position, the point inside the medium where it is changing. You need to know the density and volume of your ground to know what kind of acceleration and the gravitational constant again. And from this, you could then maybe estimate how the seismic wave is producing acceleration on your test masses. And as simulations have shown, that if you have a surface wave, the Newtonian noise contribution can be suppressed if you go underground. This is, for example, the projection for minus 700 meters. Just because the surface wave produces the highest mass density changes in Earth. However, body waves are not suppressed by going underground. So the influence of body waves stays the same. If you have a detector on the surface, you will be limited by surface waves, but if you go underground, surface waves are suppressed, but body waves are not. And since they are bypassing the isolation stages, we can also not do anything against this, and we have a huge problem. So the idea is, instead of isolating it, we need a cancellation system, a smart cancellation system. And the idea is to measure the source, so the seismic displacement, estimate the acceleration on the test mass, and use these auxiliary data to process the gravitational wave data and cancel it out in post-processing. And this is what I'm going to talk about on Tuesday about. So on Tuesday, I'm dealing with ground and ground-based gravitational wave detectors using distributed optical fiber sensors and new kind of these. And I will also talk about Newtonian noise cancellation and what kind of seismic sensor arrays might be useful. Yeah, and with this, I'm coming to my last slide. Just a short conclusion about the Einstein Telescope, the third generation of gravitational wave detectors. Any information that is given in my talk can be found online. So there was a design study about 10 years ago, and there's everything written down about the concept, about the noise sources, so we went through all of them. And it's not me alone, so this is just a map of Germany and the different institutions which are developing technology in Germany, but of course we have it also spread over Europe, for example, the ET Pathfinder in the Netherlands and so on. And I haven't mentioned other gravitational wave detectors, but if you're interested, Jan Harms wrote a very nice review paper about low-frequency gravitational wave detectors, which also include torsion bar experiments and atom interferometers, and also mentions how Newtonian noise couples into these different systems. And recently, they also submitted a new paper, but it's only on arXiv yet, for a lunar gravitational wave antenna. So this wants to measure the elastic response of the moon to a gravitational wave by using a seismometer array. So also very interesting how to, for example, use other systems to measure low-frequency gravitational waves. Yeah, otherwise, you can ask me every question until Tuesday, and then I will give you an update on Newtonian noise cancellation systems.